So there's this new sort of relationship that we have to look at when we're talking about Kb and Ka. So we call it the Ka-Kb relationship. Now, essentially, our Kw is equal to our Kb. So I could show you a big long mathematical expression to show you why this works, but essentially all that happens is if we were to multiply our regular sort of expression of Ka times our Kb or our products over reactants of both of those reactions, I would get something that sort of simplifies that. I would have my hydroxide ions multiplying by my hydronium ions. And this formula we know equals Kw. So because I can do this equation here, I can also do this guy here by multiplying my Ka times my Kb. So we can use this formula to find a way to calculate Kb if our Ka is given. Now, when we look at our data booklet, our Kas are all given to us on the right-hand side of the table as our acid ionization constant. So it only is in reference to the acid, the conjugate acid of the pair. So if I look at an example below here, I have solid sodium benzoate forms a basic solution. It says determine the Kb for this weak base present. So I'm going to show you what this means and how we can use this expression to solve for our Kb. Now, again, our first thing that we have to do here is write out our dissociation equation. So we have sodium benzoate, which is Na, and benzoate is C6H5. COOH. Oh, sorry, COO. There we go. And this dissociates into sodium and benzoate. Okay. So this is what we would consider to be a complete dissociation equation, and then we can look at the reaction of our base here. And again, I know that sodium from other examples is a spectator ion, so I don't even include that when I'm looking at my table. So I'm going to write out my equation here with my benzoate and water. So I have C6H5 COO minus plus my water, forming my hydroxide ions and my benzoic acid. Okay, so there is my equation for my sort of Kb, or where I'm going to calculate my Kb. Now, I'm going to go look at my data booklet here. We're going to take a look and see if we can find our benzoic acid. Now, it's right here on our table. All right, and what we see is that we find benzoic acid, which is this guy here. We know that benzoate, or benzoic acid minus this hydrogen, is its conjugate base, which is this guy listed right here that I've circled. Now, this value of 6.3 times 10 to the negative 5 is the Ka value, which is only in reference to this number here, or this entity here, which is our benzoic acid. So we have 6.3 times 10 to the negative 5. So if I go back, okay, I know that my Ka for this guy here is equal to 6.3 times 10 to the negative 5. So in order for me to calculate my Kb, I can rearrange this formula up here to solve for Kb. So if Kw equals Ka times Kb, then when I simplify that, Kb equals Kw divided by Ka. Now, when I'm looking at this equation, when I'm talking about Ka, I always find the Ka of the conjugate acid. That is very important. There's some entities that are polyprotic, so you might find the acid formula in the base column, but you don't want to do that. You always want to ensure that you find the conjugate acid of the base you are looking for. So if I'm looking for my benzoate, okay, I need to look for benzoic acid. I need to look for this entity plus one hydrogen to find the Ka, the corresponding Ka. So when I go to plug this in, I have 1.0 times 10 to the negative 14 divided by my Ka value of 6.3 times 10 to the negative 5. When I go to plug that into the calculator, I should get something like 1.6 times 10 to the negative 10 as my Kb value. So we can use this relationship here in order to help us solve other problems to calculate our Kb. Once we have our Kb value in this way, we can use it to solve some further problems. For example, we can use it to use our algebraic ice table to calculate hydroxide ion concentration. So as you guessed it, probably, we're going to take a look at what it looks like then to calculate a hydroxide ion concentration, POH, and pH from the reaction of 1.2 mole per liter solution of baking soda. So I'm going to go through, there's lots of steps that we need to look at here in order to solve this problem. Now, if you didn't know, baking soda is sodium bicarbonate, which is NaHCO3. All right, so we have NaHCO3. It's sort of a weak base that we have, and many of you probably have done the vinegar and baking soda reaction, so you know that it's a weak base from reacting it with a weak acid, being vinegar or acetic acid. So our first step is to take a look at our reaction here. I always like to start with my reaction. It definitely helps me give a direction as to where I need to look. So first, I have my first step. I'm going to actually do this here. So I have my NaHCO3. First thing is this dissociates into Na positive and HCO3 minus. Now, we only react our base when we're looking at this. So we have our CO3 minus, there we go, plus our water, giving us our OH minus and our H2CO3. Now remember, if you're having struggle to create these, or if you're having problems to create these formulas, always remember that if you're dealing with a base, it is the proton acceptor. It is the thing that takes the proton from this other entity in the reaction. In this case, it's water. So this hydrogen carbonate ion is stealing a hydrogen from this water ion, or this water molecule, to give you this hydroxide ion. So if you're ever struggling, remember bases are proton acceptors. Okay. Now, another thing we need to take a look at is just plugging some of these values into a table and some preliminary calculations that we can do to solve this. So again, our initial reaction is going to be of HCO3 minus, and our products are going to be hydroxide ions and carbonic acid. Now, again, if this was some sort of a dissociation where it wasn't a 1-to-1 ratio, ensure that the value that they've given you, in this case it would be 1.2 moles per liter of our solution. If you have 2 extra moles, for example, of your base, once you've dissociated, make sure you multiply this number by 2 because the mole ratio dictates that you have to multiply it by 2. In our case, we're all good and we can just plug our number into our ice table. So we have 1.2 moles per liter. Again, everything should be in moles per liter. And 0 and 0. Okay, so this time we're looking for our OH. We're looking for our hydroxide ion concentration, and from there we can calculate pH, POH, all that. So we potentially need to look to find our Ka of our hydrogen carbonate ions or bicarbonate ions in our data booklet in order to calculate our Kb. So we're going to write down our formula here just to make sure we're keeping track of what we're doing. So we're taking this formula and rearranging it to get our Kb, in which case our Kb is equal to our water ionization constant over our Ka, which means that we have our 1.0 times 10 to the negative 14 over whatever our Ka is for our conjugate acid. Now if we take a look back at our data booklet, here we go, and we are going to look to find our Ka of our hydrogen carbonate ion. So, for example, and this is what I was trying to notate before, just give me a second here and I'm just going to erase some of this extra writing on here that I don't really need or want. Okay, so when I take a look at my table, you'll notice that right here I see that there's hydrogen carbonate. Now, in this case, this hydrogen carbonate is acting as an acid. Okay, this is not the conjugate acid of hydrogen carbonate. Okay, so my first goal is to find my base in the base column. So here I see my hydrogen carbonate, that's my base, in the base column. Now my conjugate acid is this guy here. Notice it's also the product in what we formed on the previous slide there, what we formed from our reaction. So my Ka is this value here of 4.5 times 10 to the negative 7. So when we go back to our table, we have to use that value of 4.5 times 10 to the negative 7. So when I solve for my Kb, when I plug that into my calculator, I should get something like 2.2 times 10 to the negative 8. Okay, so I've solved for my Kb, which is this value here, and I know that I have an initial concentration of 1.2 and 0, but I need to solve for my OH. And in order to do that, I need a little bit more room. So I'm going to open up a note page again. Okay. So I'm going to give myself a little bit more room here. And I'll get a new page going. Okay, so if I think about my equation where my Kb is going to equal my products over my reactants, so I'm just going to jot that down, products over reactants, so we're always on top of it. Okay, I know that the products of my reaction are going to be my hydroxide ion, and based on what I have over here, my hydroxide ion and my hydrogen, extra hydrogen onto that, and I get my hydrogen carbonate, so my HCO3 minus. Okay, and that is all over my reactants, which is my, pardon me, I've mixed myself up here. H2CO3, sorry, carbonic acid, and my reactant is my hydrogen carbonate ions. So when I go to solve this or simplify this even further, I also now know my Kb. So I know that 2.2 times 10 to the negative 8 is equal to my OH minus my carbonic acid over my hydrogen carbonate ions. So one thing that we need to remember when we're dealing with our entities where we're solving using algebra, we need to remember that when we are doing this, okay, this value of 1.20, essentially this change is so small or so minimal that the change essentially does not affect this value. In other words, it would be 1.1999999 repeating, where you would just simply round it to 1.2 again. So we can write down 1.20 again for our equilibrium constant or equilibrium value of our hydrogen carbonate ion. Okay, now when we think about it as well, this is going to be increased by x, and this will be something you remember from your acid ionization constant calculations, meaning that this is going to be x, and there we go, x. Okay, so we have x and x for our two product entities, which means that we can then plug this into this equation as 2.2 times 10 to the negative 8 equals x times x. So we can have x squared over our 1.20 moles per liter. So when I go to simplify this a little bit, I get that I multiply 1.20 times our 2.2 times 10 to the negative 8 to get x squared on its own. So I get x squared equals and when I plug that into a calculator, x squared should equal 2.64 times 10 to the negative 8. Okay. So when I look and I'm looking to solve for x and I have x squared, I need to take the square root of both of these things. So if I take the square root of x squared, it's simply just x. So x. And when I take the square root of 2.64 times 10 to the negative 8, I get 1.62 times 10 to the negative 4. Okay, so this is equal to x, which means this is equal to my hydroxide ion concentration. So let's go back over to this guy here. And just see if I can select. Here we go, I'll just do it this way. So x is equal to, now I don't remember my value, 1.62 times 10 to the negative 4. So x is equal to 1.62 times 10 to the negative 4, 1.62 times 10 to the negative 4. So that's only part of my solution. This is only part of what the question is asking me. It's asked me to calculate my concentration of my hydroxide ion, as well as my pH, and percent reaction. So there's a few more things. I'm just going to go back and solve these now on this side here. So if I have my hydroxide ion concentration, I can calculate my pOH. So my pOH is going to equal negative log of my hydroxide ion, which means I have the negative log of 1.62 times 10 to the negative 4. And when I plug that into a calculator, my pOH is 3.79. So let's see. Oops. So 3.79. We'll just write that down. So this is our pOH. Now, our pH, I'm just going to have to get a new page here. So our pH is then equal to 14 minus our pOH and we have 14 minus our 3.79, which equals 10.2 as our pH. Okay, and when we go to calculate the percent reaction, essentially what we're doing is we're looking to see how many hydroxide ions are present. So how much hydroxide was created from, or as a percentage of our initial base. And our initial base was this guy, our hydrogen carbonate. So when we look at our hydroxide ion concentration, okay, and of course we're going to multiply this by 100 to get a percentage, but we have 1.64 times 10 to the negative 4 as our hydroxide ion concentration over our initial concentration of 1.20. Now when I plug that in, I should get 1.36 times 10 to the negative 4. But remember, I'm going to multiply this by 100% to get a percentage. And when I do so, I get 0.0136%. So this is my percent ionization, or my percent reaction of this equation. So really 0.0136% is a very, very small amount of our hydrogen carbonate ion turning into our hydroxide ion. Now that does make sense because it is a fairly unconcentrated and a fairly weak base to react with, and it's very weak in comparison to our hydroxide ion concentration. So we will just take a look back here. So that is how you would go through solving something like this. Okay, you would initially solve for your Kb, which then you can plug into your equilibrium expression to solve for your hydroxide ion concentration using that algebra that we've seen before. Okay, so we can go through one more example here. Oh, no, sorry. This is the same example, which I forgot I had that slide there. Oh well, we did it on another slide. That's all good. So then it says, what does this mean for amphoteric entities? So amphoteric, again, meaning that it can act as both an acid or a base. So essentially we can have something like our hydrogen carbonate that can be a proton donor or a proton acceptor. And what does that mean for a reaction? Which reaction maybe is the most important one? So essentially what we do is we can compare our K values, either Ka or Kb. So we're going to say Ka versus Kb. And we're going to figure out which one is the predominating reaction, which one is going to be the one that takes charge, it takes over, it masks the other reaction. Okay, so if we take a look at an example, okay, we can take a look at the example of let's say, let's go with hydrogen sulfate. So let's look at a full example here. So if we have something like sodium hydrogen sulfite, okay, this again dissociates into sodium and this guy here. And again, this is going to be our basic entity. It's going to be the thing that reacts. Now, when we are looking for this, again, we're looking to calculate the difference between our Ka versus our Kb. So we can simply find the Ka value for this entity just by looking at our data table, and our Kb we can calculate by going Kw over our Ka. So let's take a look. Again, I'm just going to erase some of this stuff that we really don't need on here now. Okay, so we're going to look for HSO3 minus, or the hydrogen sulfite ion, and we're going to look at it as an acid. So when we check it out, we see here that the Ka of HSO3 minus is in fact 6.3. Okay, now when we're talking about our hydrogen sulfite, we have to again be careful. Because it is an amphoteric substance, I can't use this value because the conjugate base is this guy. Well, we wanted to find our HSO3 minus as a conjugate base. So if we take another look, one step to prevent any mistakes from happening would be to actually do our reaction with this. So our HSO3 minus, okay, if this is reacting as a base, we're going to get our OH minus and our H2SO3. So when we're looking for a Kb value of this entity, we need to search for H2SO3 on our data booklet. We need to find it with one more proton when we're going to calculate our Kb. So our Ka, we can write down, we do know that it is 6.3 times 10 to the negative 8. However, when we go to calculate our Kb, we need to find the conjugate acid of that. Now again, the conjugate acid is the entity that has one more proton. So our Ka, again, let's go back, is 6.3 times 10 to the negative 8. I know that because I can simply just find our HSO3 on my table and look across and find that number. Now, if I'm looking for my H2SO3 as an acid, that is my conjugate acid that I'm dealing with. This is the conjugate base. So when we're calculating our Kb, we need to use the base component of our conjugate acid in order to figure out which value to use. So I can't simply plug in that other value. So I'm using 1.4 times 10 to the negative 2. So this equals my Kw, which is 1.0 times 10 to the negative 14, divided by 1.4 times 10 to the negative 2, giving me a value of 7.1 times 10 to the negative 13. So when I go to take a look at these two values, okay, this guy here and this guy here for Kb, I need to figure out which value is larger. Okay, so the Ka value that we see here, okay, is 6.3 times 10 to the negative 8. Now, relative to this number here, 7.1 times 10 to the negative 13, negative 13 is a very significantly smaller number than our negative 8. So our Ka value for our hydrogen sulfite ion exceeds, it masks this other reaction. This reaction will happen more times, or it's more frequent, and we create more, for example, hydronium ions than we do hydroxide ions, which means that our Ka value, because this is the larger of the two values, it is the predominating reaction. It is the reaction that we see most often, and if this was to be in sort of a vessel or a container that this reaction is occurring, the Ka, or that this acid reaction, is going to happen more frequently. So again, you have to be careful with those. When you're calculating calculating Kb, you need to use the Ka of the conjugate acid. Remember that conjugate acid is the entity that has one more proton than our base that's given in the example. So again, write out those equations, help you to figure that out. And then the Ka is the entity that should be the easy one. It should be the one that we can just pull right off the table, no calculation required, and we just look at for that entity in the acid column of our table to compare these. Now, of course, there's several amphoteric entities. Most of them, like we mentioned in a previous lesson, are hydrogen polyatomic entities. So it's hydrogen with some sort of polyatomic ion giving us this type of substance. So calculating Kb isn't so different from calculating Ka. We've just added another little extra step in there. Now, recently, they do tend to sort of add in some of these examples onto a diploma exam. So just be sure you're familiar, especially with this equation that I'm writing at the top here, that Kw equals Ka times Kb, because those are the types of things that they like to add in on diplomas, just to make sure they're really testing what you know, and really taking it to the limits on how much you guys have learned in Chemistry 30. All right, well, if you need to rewind or go back in this lesson to rewatch or take notes or anything like that, please do so now, and good luck.